Welcome everybody to a SkyCiv tutorial. Today we're going to be looking at how you can design a bracket using plate elements in SkyCiv Structural 3D. So I've got an example here that we're going to use. We're going to just design it in 2D, but just as easily you could design the 3D bracket as well. But yeah, for example's sake, we're just going to go through this 2D version of the bracket, learn how to apply loads, how to mesh the plate, and how to generate the geometry that we're going to use in the analysis for this particular element. So today we're going to be mainly using SkyCiv Structural 3D, but we're also going to have a bonus look into the SkyCiv FEA program, which shows you how you can design this bracket with more accurate 3D brick elements. But for now, let's look at S3D and how we can build it using shell elements. So we're going to use 2D elements, and it's 2D because it is a plate element. So we're going to just start with some basic geometry. So first I'm going to look at my unit system. So it looks like we're using millimeters, makes sense, it's a smaller bracket. So I'm just going to switch that using my unit system, just switch over to millimeters. Okay, and then we're going to start by adding in nodes, and nodes are going to be the edges of my plates. They're going to be where we apply the point loads. They're a really important part of the model, and we're going to just start by plotting these nodes around sort of the edges of these plates and use that as the boundary of our plate. So I'll just start with the 0, 0, 0. Now I could just continue to plot, so here obviously we're going to go up by the thickness of this element, which we don't really have a measurement for it, but for the time being we're going to just assume it's something like 90, looks like about 90 millimeters there. So we'll go up in the Y by 90. And then it's 450 wide, and then again we haven't really got a measurement for that, but we'll assume that's 90, so 450 minus 90, and you can put in operations here, so we'll just do minus 90, and we'll do 90 in the Y, and you can see that's put it in there. So this is pretty useful. You can put in operations there to do the maths for you. So yeah, so we have sort of 4 nodes there, and let's just generate a plate here just to show you how you can do it. You can just highlight those nodes and you can just right click add plate, and you'll see that will put it in the correct order and create a plate there for you. So we've got that bottom part of the bracket. Now let's add in this other bit, and I'm just going to show you another way that you could generate those nodes, particularly if you've got a little bit more of a complex shape. I'm going to use the pen tool, and with the pen tool I can actually turn the snapping to a smaller increment, so say 10 millimeters, and I also won't connect the members. So rather than connecting members, I just want to drop a node at certain locations. So I'll start with this one here, and I can use the pen tool to snap to grid to the nearest 10 millimeters, and looks like it's 300 millimeters in the Y, so let's go 300, and that just makes things a little bit easier. I can get 90, let's snap to my grid there, and same as I did before, I can just highlight those nodes and add the plate, or another way is just to go plates and just go type in the nodes, so 4, 6, 5, 3. Okay, so we've got those 2 plates there. Again, using the pen tool, I'm just going to add in some other nodes here. So we're going to say go down. We don't really. Oh, we have a measurement there for 50 millimeters, so we'll go down 50 millimeters. There, so it'll be that one. Don't really have a measurement there, so we'll normally work that out. But for now, let's just go down. Call that 90. I can also use that to understand how far we're going from there. Okay. Let's go 70, and then 90 from there. So plates there, let's go 7, 8, 9, and 10. So quite easy there. We've got 3 plate elements. If you did have more than 4 nodes, that's fine. You can add multiple nodes. So if it's a more complicated bracket or shape, you can definitely do that using the software. And we're also going to support it, so there's a few ways we can support this frame. I'm just going to start with some basic supports and then show you how you can kind of develop and improve the model. So we'll just put some supports at 1, 3, and 5, just pin support, something like that. And then we will apply a load at node 10. So point load, node 10, and we'll do a 10 kilonewton load there. Now the most important part of generating a plate element structure such as this is the mesh. So the results are going to directly depend on the quality of mesh and how everything is connected in your system. So I highly recommend when you go to mesh a structure like this, or even a larger building where you have a lot of plates, that you mesh them all at the same time. And what this will do is it will preserve and connect any internal nodes, any members that might be associated, like linked or connected to that plate, or even any edge plates, edge nodes here. So if I mesh these individually, I might get an issue where this node isn't actually connected to any part of this plate. Whereas if I mesh them all together, the software will automatically know, okay, there is some edge nodes here. I'm going to connect this plate to those nodes, even though they aren't making up any part of my boundary box. So I can show you an example of what that would look like if I mesh them one by one. So I'll just go, you can right click the plate, just go mesh. And because it's not quite rectangular, I'm going to use the unstructured quadrilateral. So that will just leave it up to the software to calculate the mesh. And I'm just going to go for somewhere in the middle in terms of granularity. So obviously you can go very fine or you can go very coarse, and that will affect your results. But for now, I'm just going to leave those as they are. And you can see it has picked up these edge plates. So if I mesh that now, I get a nice mesh there. I'll just turn the mesh nodes off, just to get some clarity there. And then if I was to mesh this separately, so I'll just mesh that down. Actually, in this case, the software has detected these edge nodes, so it has connected the elements, but that's not always the case. So you can get a scenario where maybe this node isn't connected to this plate, and then if that's the case, you won't see the transfer of load from this plate to this plate. You'll get some kind of discontinuity or some issues with the connections there. So the software in this case has detected that there were these edge nodes, so it is able to do it, but it's just something to be wary of, that sometimes you want to mesh the whole structure at once. So I'll just show you how you can do that. I'm just going to Control A, and I'll just unmesh everything. So we start again with the plate. Just Control A again, and then mesh plates. This time I'll mesh them all at once. And you should see proper connectivity between the two plates. So you saw in both scenarios it still did work, but it's in some cases it might not be as clear to this plate that this plate is connected to it. So sometimes a good idea to mesh connecting plates at the same time. So that will pretty much give us all we need to run an analysis. So we've got a point load. We have the mesh correctly set up. The quality of the mesh looks pretty good. They're all evenly distributed or evenly sized mesh elements. So you typically want to look for that. You don't want to see any very slender elements connected to sort of more rectangular elements or square elements. So we're seeing a pretty good quality mesh there. And I think we're pretty much ready to run a solve. So I'm just going to go ahead and solve that. Okay, so we've done a static analysis, and we can now start to look at some of our plate results. So I can see by default it'll show the deformed shape, and I can have a look at the displacement sum. Typically what I look for first is just to make sure that there is proper connectivity between the plates, and I can see that they're all moving together. So I do know that my nodes are connected correctly, and it is displacing in a manner that I would expect. So I've got a downward force and it seems to be displacing in that way. Then we want to look at the stresses. So the stresses are a really important part of the design. I had just some default plates, so we can have a look. Sometimes it's good to look at in 3D and just get a feel for how wide the plate is. By default, there'll be a plate thickness. So I've got just a 5mm plate thickness. I'm not sure if there is. It doesn't look like there is any thickness to this plate, but if I wanted to change that to say 10mm, that would obviously affect my results too. So I can just highlight them all, change that to 10mm, and I can do that all in one go. And the great thing is I don't have to remesh it because it just is a plate element, and I've applied the mesh to my plate. It automatically connects the plate elements to all those children mesh elements. So I don't really have to change anything else. I can come back now and go to my plate results and start to look at some of these stresses. So I'm seeing the stress reduced, obviously because we added more material to the plate elements. And I'm sort of seeing some peak or some heavy stresses around the supports at about 146 megapascals. Von Mises is a really good indicator of the stress. We have a great tutorial. I'll drop the link in the YouTube video comments below. But you can also find that from our documentation. And just by searching plate results, plate analysis results, some keywords there. And we've got a really great video and tutorial explanation here, just explaining all the different plate shell element results, as well as some local axes definitions and things like that. So you can always just search our documentation, you can close that window and just get straight back to your workflow. So I hope that does help. We also have some major and minor stress, principal stress results, and you can see sort of one of the sort of larger stresses that we're seeing is around 160 megapascals. And I can have a look at the material used. So two things I want to look at for actually. One is the material used to see what the ultimate limit and the yield limit is for that particular material. And also just want to see the type of stresses that we are receiving. They're quite concentrated. So that is a bit of an indicator that maybe we've applied the load at one concentrated point, or it is an indication of a weak point of the structure. So I can see that there is some large negative stresses here, especially if we go to the von Mises. We'll see some peak stresses up here in this corner, so where the supports are and then where the point load is applied. And so just to explain that, the material usage too, so when I created this plate, I had the plate thickness and I also had a material ID. So this just tells the software what material properties to use. So that's got material ID 1. So if I go to material ID 1 for structural steel, I'll also see just the Young's modulus, the density, as well as the yield strength and the ultimate strength. And we had a yield strength of about 140, so that was a good sign. The structure wasn't undergoing any significant yield, and it wasn't reaching that limit state that we have there. So yeah, typically we don't want the material undergoing more stress than the yield, otherwise you sort of see that permanent deformation. And yeah, it's something definitely to look out for, is the material properties are going to directly affect the results that you receive, so definitely worth checking those before you proceed with the analysis. The other thing I also wanted to go through too is just those concentrated loads. So in this case we do have 2 pin supports. We can also apply, just delete those, a line support. So maybe this is a different system where we have, we had 2 pin supports, but we can also use a line support. So maybe the bracket is supported between nodes 3 and 5. So you can see that's a little bit more rigid. And another issue which we might have noticed is that there was a very, very concentrated stress here because that's where the load was being applied, where in reality that's probably not going to be concentrated to a specific small point on the structure. Very rarely will you have a contact load at a really finite position on the model. You'll usually have it spread over a contact point on a bracket or a plate. So what you might want to do is, there's a couple of things you can do. But say this was a directional load, because we can also look at what happens if we apply the load in the X as well. 5, so more of a diagonal load. And what you can do is split that load and apply it to the different nodes. So we'll just turn these nodes back on. So you could separate the load and maybe apply it over 4 or 5 different loads, but then you have to kind of copy and paste the load, and if the load changes, there might be a little bit to change. But another thing you can do is, let's just introduce a new node here. So we'll delete this load here and go back to our trusty pen tool, and let's just introduce, it can be 10 mils up, maybe 20 mils up, something like that. And what we can do is apply the point load here. So you can just click that. You can right click it too. Add point load. So it was -5 and then -10. And what you can actually do is connect this as a rigid link. So I'm just going to connect an element between those and just change this element type to rigid and apply that. You'll see that goes to the letter R, and what that does is creates an infinitely stiff element. So we're going to actually change the distribution of this member to connect to all of these nodes and distribute the force among all these nodes rather than just applying it to a concentrated point. And I could have chosen any distance. This node, I went up 20 millimeters. It doesn't matter, but because I'm connecting it by rigid elements, so they'll automatically transfer all of the load, bending moment, shear force, everything from this node to these nodes, so evenly distribute the force there. Sometimes you want to look out for eccentricities, but for the moment they're quite small in this case. So this is a good way to evenly distribute a point load to a number of different nodes, and sort of see a more realistic stress profile on those particular plates. So this is an also very important thing to look out for. So you want to you can't have the same node acting as a master and a slave. And probably I've got this point where this same node 1449 slave to all of these. I think I need to reverse the order of all these, or maybe it's just this one. Let's try this, just this one. Okay, so I think we have to replace the order of all of them. So we can just use this reverse node button. Apply that. So probably the best thing to do in this scenario is just to drag from the rigid node, the node that you want to connect the point load, out to the mesh node. So that way you avoid having to change them all back. But that reverse node feature makes it a lot easier. Okay, so now you have one master node for all those rigid elements. So I'm getting better results now. I'm seeing that it's solving, and now we can review the stresses. So this is member stress. So just remember to go to plates, and now we're seeing much less stress, much less concentrated stress. I can see it's a little bit more spread out along all this part of the model. Also some concentrated stresses there. I'm still getting a bit of concentration around this support. So I might want to do the same trick of connecting a support to a few nodes here based on these rigid links. But I'm also getting a clearer or a more distributed stress profile along this member because it's not as concentrated at these two ends. And I can also see that as I'm deflecting the structure, this support is remaining rigid. So I can see that that's kind of where the bracket is being supported from. And yeah, the stress has come down a fair bit. So we're not concentrating that load all in one location, and hopefully getting more accurate results to use here. So as a next step, I can always create a 3D version of this model. So let's just turn off the plate nodes and let's just Control C, copy all that. Okay, and I've got a reference node 45. So I can either use that as my reference node there. So that's going to be where, if I paste, it's going to paste that as my reference node. But kind of want my node to be this one here. So let's just do that again. Control A, Control Shift C. And then now it's saying, okay, you've copied your whole structure and saying select one node to be your reference node. So I'm going to choose node 1. So now my whole structure is copied with my node 1 being my reference node. And this makes life a lot easier because now if I want to paste, say I want to make the bracket say 100 mil wide, maybe 200 mil wide, I can now paste and I'm going to make it negative 200 in the Z. So I'm going to use this as my reference node. So I was able to paste that. So now I can see I've got the bracket sort of taking shape in 3D space. And let's also just create a plate here. So right click, add plate. So I have a plate element there. And let's also create one at the bottom as well. Just highlight these 4 nodes. Add plate. Mesh that. Once again, just want to check everything is connected properly. Looks like it is. I can check that in the analysis results as well. And I can also, if I wanted to, use some of the operations. We have hole cutouts as well, so you can add a cutout or a hole, plate hole there. And you would need to do it when it's unmeshed, so that way it can mesh around that hole. We've also got some other operations when you're building the geometry, such as, well, we saw a bit of the copy and paste, but also some of these geometries like curved members. You can use that to create more curved plates, mirror rotate, things like that, that just help construct the model. But pretty happy there. I think the line support, maybe we'll just add in another one. I don't think I copied that one across. So let's just go supports. Can double click there, line, sorry, double click there. So now I've got 2 line supports. And yeah, pretty much ready to solve. Okay, so this is maybe one of the errors that you will receive, particularly when you're meshing plates individually. So let's try to maybe just remesh everything. So we're just going to unmesh the whole structure. We still got all the core parts of our model, so we still got all the rigid links. The software has recognized that those nodes are being used elsewhere. The edge of our plates, the line elements, so the model is completely still intact. I can just remesh now. Okay, we're just going to mesh them all together. Okay. And again, we're looking for similar results, looking at the von Mises stress, but now we've got a 3D model that accurately depicts how that bracket will deform and what kind of stresses it will undergo under those particular loads. So everything can be modeled and analyzed within SkyCiv Structural 3D. Yep, just using the plate elements. You can sort of turn on some of these if you would prefer to see them in a particular shape. Yeah, so that's pretty much it. That's how you would model a 3D bracket element, bracket using plate elements in SkyCiv Structural 3D. I hope this tutorial has been very useful, and we're going to stay on if you want to look at a bonus way how you can model this in our FEA program. Thanks. As a bit of a bonus, we're going to look at how you can build the same bracket using the SkyCiv FEA program. So we're going to start by importing a DXF file. Now you can use any DXF file here. We're just going to import a 2D drawing of the bracket that we're looking to extrude and design. So you can see that we're extruding it over a 2000 millimeter line, but you can see that 2D DXF element has been extruded throughout that that line. And then what we want to do is just kind of assign the edges as being some part of the shell, some shell elements. So we're going to give them a thickness. And then we're just going to change that 2000 millimeter length to something a little bit smaller to represent the actual bracket. And you can see I've included a 80 mil and 20 mil panel. And the reason for this, which we'll show you now, is that you might want to put in some other elements such as holes or cutouts. So you can see here I've just cut out that middle 20 millimeters. And yeah, so that might be some hole representation. Then I want to just select the edges of my plate. I can also use the node select tool, and this is just going to be the outer edges of my bracket. So I'm just going to select those edges and provide some thickness. So I'm just using a 10 mil thick wall for all parts of the bracket, and just going to do the same for that internal sort of brace element. And then I'll just copy and paste and do the same on the other side. So you sort of see that bracket is now taking shape. This is still using shell elements, but it will do a sort of closer analysis. It's quite similar to the S3D one, but we can do a lot more in terms of the analysis, and yeah, even things like the cutouts are a little bit easier to model. So you see we've generated a mesh there. We've got quite a few options in the mesh, and then once we've meshed, we can then assign boundary conditions and loads. So I'm just going to select the outer nodes here of these holes. So that'll be where some bolt or some fixity is added to the bracket. And I'm just controlling the degrees of freedom there, just turning them all on, all 6 degrees of freedom. So it is restrained in all directions and rotations. Then finally, I'm just going to add some loads. So you can just use the polygon tool to assign which mesh elements you want to assign the load to, and just putting a negative 100 kilonewton force there will distribute that force across all those elements. So you get more of that gradual load being applied rather than a concentrated load to one node or one point. Then I can run a linear analysis on the bracket. So this is still a shell element, but you can see I get a few more results I can review. So I've got the same von Mises stress there. Obviously applied a larger a larger force there, so we're getting a lot more stresses than the original S3D version. And you can do a linear buckling analysis, so you can go a lot more in depth in the shell element analysis that you're running using this tool. So you can run a plate buckling analysis. You can also do linear, non-linear for both. Sorry, you can do non-linear geometry and material non-linear analysis. And here you can see it's running a non-linear explicit analysis. And you can also chart specific areas too. So if you want to review sort of the forces or the results in those more concentrated areas, you can do that. And as it steps through and runs the non-linear analysis, you can see it will graph the curve for you to review. You can pause or abort the solving at any time, but you usually want to look for some convergence. So you can sort of see it's starting to take shape now at about 50%. You start to see it yield. Okay. So at that point you might want to abort the linear analysis, non-linear analysis, and start reviewing some of the results. So you can see it still carries through the steps, and you can still display the analysis results for that particular step. also your plastic strain results as well, with some limit to the strain. So there you have the final shell model built and analyzed using the SkyCiv FEA program. So feel free to leave any comments in the video below, or if you have any questions, feel free to email us at support@skyciv.com. Thank you.